Yeah, thank you. It's been a pleasure being participating of this workshop, and I do want to thank the organizers to first organizing this. Right? It's very well put together program, and for inviting me here, right? And also, of course, for ITAMP for hosting, right? This workshop. Like Johannes mentioned, right? My talk, it's basically some of the theoretical aspects of the research, right, on three-body recombination, the product states, three-body recombination. I'm gonna try not be so to be redundant on the things that he has already said, but probably is gonna have some overlap here, right? I do want to make a few points, though. I think that we have seen, right, the research in ultracold atoms and molecules, right, moving towards more of a chemistry, right? Part of the research, the ultracold atoms is reaching so many different branches these days, right? And of course, this is leading to a different kind of chemistry, right? The ultra-cold temperatures allow you prepare your reactants in a very well-defined quantum state, and quantum statistics it matters. But in a way, all these what we are calling chemical reactions these days, right, they have been seen from the from the beginning of research on ultra-cold atoms, right? They were always there, but they were seen more like, well, losses, right? These chemical reactions, the products, they come out with a lot of kinetic energy, they cannot be trapped, and then you see your atom number or molecular number decreasing, right? So that was not a desirable thing, and actually, we benefit a lot on the theoretical side. We study these rates, all these loss processes, the dependence on the scattering, on the statistics of the system, and there's a lot of great stuff. But we don't learn much about the actual dynamics of the reaction, right? To do that, right, is what people are doing these days is the state-to-state chemistry. Right, because now you know your initial state and your final state. By doing this, right, we believe that we can learn much more about the chemical process itself. Right, that's the whole idea here. Right, I pointed out a few of the groups that do that. There's more, right? Of course, in this talk, I'm going to be talking about three-body recombination. We know already atoms collide and form a diatomic molecule in a free atom. Okay. Our theory team is this one, right? Paul Eberhard, myself, and Jing Lu on the theory side, right, doing the simulations and so on. I'm not going to go much on how I do my calculations. I have a few slides. If you want to know more about the details of the calculations, I can go over that during the questions. But they are fully quantum mechanical. Right, we are doing the least amount of approximations as possible. We are using as much of the real interaction of the problem. We use the hyperfine structure, and it's highly non-perturbative, right? And of course, it's a very complex dynamic. So, because of all that, I believe it's necessary to have a unifying picture, a picture that a clear physical picture of the process that can help us to understand what is happening. And I do believe that the hyperspherical adiabatic approximation or representation is the one that can provide the most of the information possible there. Right. In the case of three-body recombination, right, I want to show you a little bit of how we think that in the hyperspherical representation. Right, we said have a set of potentials. Right? Those are like any regular potentials you know for diatomics. Right? But now the hyperage describes the overall size of your system. Right? You have a series of curves here. Those are continuous states. They have centrifugal barriers. So those are the initial states of recombination. And the states down here with negative energy, they are the outcome states. Those are associated with a diatom and an atom state, right? And in our particular case, we are studying rubidium, right? Sometimes 87, sometimes 85. And we have the rubidium atoms in a spin stretch state, right? Because this is the one more convenient for losses. And in our case, right, for recombination, we have 3 atoms colliding, so they go towards this, the short range here, in this gray area is typically the van der Waals length, right, or twice of that. And in this region, we call it, that's the reaction region, is where the inelastic transitions happen, right? And from there, they should follow some pathway to reach a given final state. In our case, like was said before, right, those are diatomic rubidium, right? Those are rubidium dimers, right? And they are characterized by vibrational and rotational quantum numbers, but also the hyperfine quantum numbers, right? Here I have F and MF. F is being the two-body total angular momentum, and it is projection. That's the spin state in which I'm going to label a lot of the molecular states that we are going to be moving on. Okay, our idea here is really whether or not we can find simplicity. Right? I mean, this is a highly complex. It is really hard to know beforehand what could happen if one state could be more favorable than others, the other state. We don't know. We didn't know when we started. We didn't know if there were going to be vibrational, quantum number dependence, rotational, and none of that. Right? The only thing that we knew, of course, that all this will require us to look to the short-range physics that we haven't done much seriously before, what we have done now. The only thing that we can say here, right, is that the total hyperfine spin should be conserved. Right? The total, meaning the three-body hyperfine spin should be conserved. So if I start here, any other state that I have to finish, that has to obey this guy. Right? But that's a trivial one, right? And what we found is actually a little bit counterintuitive in that sense, because that's the only quantum number that is conserved. Right? Of course, the total orbital angular momentum is also conserved. But the first propensity rules that we identified, right, based on experimental data and calculations, right, was what we call the energy scaling propensity rule, right? Is basically to say that the likelihood of forming a molecule, right, it depends on the molecular binding energy, and the probability goes like 1 over the binding energy, right? I don't think that was known, right? In our both theory and experiments show clearly this behavior. Here in this figure, Johan has already shown his talk. So just these are the recombination, the partial recombination rates, three-body recombination rates for class of L equals 0, dimers, L equals 2, 4, 6, and 10. Okay, and we are shifting all this. All right, so you can separate the different partial waves, but they all, without this scaling here, they all would be on top of each other. All right. And this line here is the 1 over the binding energy, right, that we are talking about. The color ones are the experimental data, and the black symbols is the theory. All right, so it's a fairly good agreement in that way. But the most surprising result at that point for me is that there were no dependence on the rotational state of the molecule. Right? So I can come with 3 atoms very slowly, and I can form with high probability, right, a dimer that has L equals 10. Right? And this L equals 10 state is going to basically have the same chance to be formed than L equals 0. So there's really no propensity rule for the angular momentum of the dimer. Right? That was a little bit counterintuitive. Right? But we built a little bit of a simple model to understand most of these effects that we see here. Right? This is still in preparation for a few years. Right? So I have to finish this. I mean, I just need to put it out there. But the idea is trying to trace back some of the pathways that recombination, you can go from 3 atoms to a dimer. Right? And in this model, what we find is a form of our LO3. that depends, that goes like one of the binding energy like we want to see. But there is additional term here, which is a summation of the different, the phase difference of the pathways that you can get to your final state, for a given final state. And of course, this one over the binding energy really is coming from the long range physics, right? And the short range physics is really embedded into this phase, right? And is this phase here, like when you look at the experimental data, you see the data is doing, there's some oscillations, there's some, that's not numerical, right? Or experimental or issue, right? This is the effect of this phase, right? For every time, if you didn't have this phase, all this should be smooth, but you have these oscillations or variations because of, there's a phase that you get when you go through your final state. And based on the numerical calculations, I was analyzing what is, how much, basically the effect of this phase here in this rate. So I multiply all the theoretical rates here by the energy, get everything flat, and then analyze this difference, which is just this guy. And I found that within a statistical treatment that they follow a Poisson distribution, right? Which is a signature of some chaoticity in the problem. This is a known process that it has been studied before too, but never for recombination, right? So there is interesting things that we are learning, right? Not just measuring the bound states here, right? But there is a lot of physics that you can get from these measurements, right? But if you should notice that I didn't say a word about spins yet, right? And that's actually for a good reason, because I want to talk about the spin propensity rules, right? For both 87 and 85, what we found is that the most likely molecular, most of the molecular states formed are those which have the same spin than your initial state, right? In the case of rubidium-85, which is this one, right? The atoms here, they are in the 2-2 hyperfine state. And you have molecules that are in this state, the 4-4, 2, 2, which is exactly 2-2, 2-2. All right, so this is a molecular state that has the same spin quantum numbers of the pairs of of your initial state. So this is a very strong. It's basically saying that even though only the three-body hyperfine state should be conserved, the two-body in this case is also conserved, right? And it has no reason to be, right? That's why it is a propensity rule, right? In our numerical calculations, we can see how strong this propensity rule holds, right? This is for rubidium-85. The red stars here are the favorable states, and all the other ones are states with different hyperfine. And you can see there's a factor, basically a factor 20 in difference between the favorable and the unfavorable states. You even have states here that you don't follow the usual binding energy scaling law, right? And those are states where you are changing the total F. So it's a higher order process to form those states. So in fact, again, well, this doesn't have a rotational dependence and so on, but it's really the spin propensity rule that is starting up, opening up ideas to control the chemical reactions and the things that Johannes was talking about. Both of the schemes that he presented depend on the spin propensity rules, right? Because, and we did the studies, we generalized these studies for all the alkali species, right? We found that these spin propensity rules, they are modified. Rubidium-87, 85 are actually special cases, right? Lithium is another special case where everything becomes much more complicated, right? So we did, and we understand much better today what is controlling these spin propensity rules, right? And again, this is the gateway to introduce control in the system, right? We idealized two different schemes to control the interaction, the product states, right? And they are fundamentally different, right? In the first scheme, what you're doing, you're modifying your initial state, right? So you want to modify your product states by modifying your initial state, right? You can do that, right? That's one way, right? We introduce some form of a spin mixing. I want spin mixing because I know this spin propensity rule and how important it is. Now, the other way, it is to mix the spins in the final state, right? Again, the spin propensity rule, it is actually telling me it doesn't matter if I'm changing the initial state or the final state. If I'm changing the spins, something should happen. Right? In the first case, by controlling the mixing in your initial state is the case where Johannes present there near Feshbach resonance. Right? Our theory expectation was that for away from the Feshbach resonance, right, the atoms, this is the favorable state, right? It was the same state that the atoms are, right? But when you bring away, the system close to the Feshbach resonance, now you're going to get this mixing with the closed channel molecular state that has, in this case, a spin 4 minus 4, 3, 3. Okay? And then you should see at this point, or as you get close to the Feshbach resonance, new molecular states appearing. Right? That's was our physical intuition. That's exactly what Johannes sees, right, in experiment. Right? He explained pretty well, so I don't need to go over this. This is the favorable state, right? We see being populated all around, but the unfavorable states, right? These two here, helical 2 and helical 0, they only appear near the Feshbach resonance, which is within this regime here. Right? Our theoretical calculations, right? They of course they show the same effect, right? But we can look at things a little bit closer, right? In this case, I'm highlighting here the favorable state in blue and the other two, the unfavorable in red and green. And you can see that away, the resonance is here at 155 Gauss, right? You can see as we approach there, there's probably some effect going on here, maybe some interference, right? We need to resolve that, and we could, if you improve the sensitivity of the experiment, because there's if the rate is too low, the experiment is not going to be able to detect, right? But if we improve that, maybe we can try to resolve some of these and try to explore and see what's going on. But clearly, is in agreement with experimental data. Even here, you see the FMOV resonance, right? In the FMOV resonance, it basically it enhances the rate for all states, no matter what. So it doesn't introduce any spin dynamics because the FMOV state is a shape of resonance. So it's just affecting the initial state, not the spins. And after the FMOV resonance, you can see that the dominant state is one of the previous unfavorable states. Right? So it's pretty interesting here. We are showing that both theory and experiment is showing that this is a reliable way for you to control the flux of your reaction, right? You can favor one state or another. The second way in which you can mix control the final products is by changing the nature of your final state, right? In this case, the molecular states. For this is rubidium-87 again. We found a case near for small magnetic fields, I would say, that there's these two molecular states, right, away from this avoid crossing. Those are the quantum numbers, so I'm calling these guys like the bare states. The picture that I'm going to give to you here is depending on, in some form, it's similar to what it would be a dress state, right? But so you have these two levels, right? think that these dashed lines would represent the energy of the bare states, right? And when you go away from the void crossing, those are the states I'm called B up and B down, right? And I'm writing the U and the L, the upper branch and the lower branch states, has a superposition of these bare states. That's going to help me to understand this process a little bit better. Right? And by doing this, right, of course, we know the overlap. We know these coefficients, how this is switching. Right? So for the U state here, okay, yeah, for the U state, when you are away from the void crossing, it is B down, and then when it's near on this side, it's going to be a B up state. Right? That's correct. Yeah. Because of in this near this avoid crossing, right? The state is going to be a superposition of two molecular states that have different spins. Yeah. The dashed lines, I mean, it's me putting that. I didn't really calculate it. This is just to illustrate. But the bare states, they are not, the B up and B down, they are not mixed. Right? It's the U and the L state, they are mixed. Okay? All right. And again, I'm just putting some labels here to help you think through this, right? Like the U state is mostly a B down on this side, the L state is mostly B up on that, and so on, right? And what is the theory expectation, right? In this case, the favorable state, right, is the state 2 minus 2, 1, 1, which is basically the state that it has the same spins of the initial state here, right? So it is the B up state. Yes, B up here. So at low field, right, the state that has the most B up is the L state, right? It's the lower branch. So this one should be more favorable to be formed on the left side of the void crossing, and on the right side of the void crossing that inverts is the U state that is going to be more favorable. Okay, that's pretty intuitive. And the question is how you go from one to another, how these things goes, right? And Johannes answered that, right? You can see the detection signal here, then see that the rates for the lower state, or the lower branch, which were the dominant here, they do have a higher rate here, and then they switch orders as you go through the void crossing, right? Again, this is showing an enhancement of a factor of about factor 30 of on the reaction rates for this the upper branch state, right? So it's a fairly substantial degree of control, right? And on the theory side, right, we look into that. And also, of course, in agreement with the experiment, there is some, of course, I should have some, oh, yes, here. The agreement is more quantitative at this level, okay? We get just a factor 10, right, of enhancement, and actually even the rates away from the void crossing, they have this factor 10 difference, right? And is easy to understand. We have to do truncations in our bound states. This is a highly rotational state, right? So we have a little bit more difficulty in describe these states. But if we wanna, can just use potential models, they are deeper, right? And so it's gonna correct things, and that should go towards what the experiments see, right? But the general trend is there, right? And that's what we care at this point, right? I start looking to this problem now, of course, that we got there, and I'm start thinking about some simple model to understand a little bit more of the physics that's going on, right? And I started thinking that this is preliminary, right? I'm thinking L3 has been calculated like in a Fermi-Gondor rule, right? You have your initial state on this side and your final state, in our case, the final state is going to be a superposition of two bare states, right? And if I develop this further, right, I get analytical formulas for LU and LL, right, for the U, the combination of the U and the L states that is going to depend on the overlap of the spins given by the FU up, FU down, FL up and FL down, but also I get a phase here. And of course, I depend on the bare recombination rates, right, which I'm assuming to be the one that we get away from the void crossing, okay? And of course, by doing that and varying this phase, we are still working on that and trying to see if we can pin down what this phase should be, or if it is really an unknown phase. But varying in this case, right, we can see that it would still cover the results. Right? It would still capture a lot of the physics. I'm varying here from 0 to pi, right? And it gives you this shaded region, okay? But I realized that this is a particular case, right? It's a particular case, right? Because one of the rates is much larger than the other, right? For the theory, this rate is this rate here is 10 times larger than this guy, right? So if I apply the same formulas now, but assuming that the rates are similar, right, then I start seeing a different role for this phase. This phase here can lead to a resonance, constructive and destructive interference when you go through this avoided crossing, right? You should look here for a given phi. You should look for curves of the same color, right? This guy, you see that for phi equals 0, you have a constructive interference before you switch from this state, and the same thing here, right? It's symmetric around this point. But for phi equals pi over 2, right? You have it has no effect going on. This term cancels, right? But for phi equals pi, you have a destructive interference, so you get a 0 on your rate. Right? So this, I think, is important. First, because we can think in new ways to control, right, what is happening through this avoided crossing. And also interesting, if you look to another case, like when the rates of these two states that are avoided crossing, they are the same. If you do that, you get very distinct behavior depending on the phase. In this case, you see that there's here a clear, just a constructive and destructive interference, and when it's pi over 2, you don't see nothing. It just remains the same. All right. So this switch and the things that we have been doing in numerical calculations is not necessarily always is going to happen. All right. And we are exploring that. How robust is this case that we have been studying? And definitely it's going to depend a lot on the coupling between these two molecular states. So we are right now looking for numerical evidence. Right? I'm coming up with a model and doing some actual full numerical calculations to see these effects coming up from there. Right? And try to get a little bit more physical insight. So I realized, yeah, I'm right on time. Okay, so this is my summary, right? I think that it has been great working with Johannes. This back and forth between theory and experiment has been very helpful. There are things that I look there, I don't know if it was the theory came first or the experiment, and we don't care, all right? We are together into this, and it has been a really fast-growing learning curve, right? And I'm going to leave you time for you guys to make questions if you have any. Thank you.
Thank you very much. Questions?
Both your free-body recombination rate and the ion count rates in the experiment, there are features.
Yeah.
Are those features resonances?
You mean this kind of ups and downs here?
Maybe go back to the one which shows, yeah, right here.
So I associate, again, you see these oscillations here, that could be that phase that I mentioned right in the beginning that is a little chaotic. Where you're changing the magnetic field, so maybe think that you're changing some of the void crossings in the two-body potentials. And at some point, some of the changes can, some of the phases can change very fast. And I see these kind of things too in the theoretical calculations, right? So, and that's something that I know that we should do. Is just this numerical heavy, but if I can resolve this, this should, because I think this should be continuous. This should be smooth functions. It's just not going to be simple functions, but it should be smooth. It shouldn't have discontinuities. Unless you have some flip of state, you could have something that could discontinue, but it's most likely should be continuous. So it's probably associated with a change on the phase on the pathway is going to that reaction problem.
So would this be somewhat related to something like known in lambda zero theory, of course, it's Stuckelberg oscillation, perhaps?
Yeah. Could be a Stuckelberg oscillation. Chris? You have a question? No?
It's probably my ignorance. You were stating that the Poissonian distribution hinted you towards chaotic behavior. What is Poissonian distributed?
What is the Poisson distribution?
You said you measure some Poisson distribution, and that hints for chaotic behavior.
Okay. You want to know what is this distribution?
What are you looking at? What is Poissonian? Because normally I would expect Wigner-Dyson distribution to hint towards, but this is something else here, so I don't know what it is.
Yeah, the Wigner-Dyson would, if it was a Wigner-Dyson for energy levels, that would be indication of a chaotic behavior.
And here it is.
In a Poisson distribution, in this case, there were a flip. If you are looking to some other things, that is the Poisson, that is the signature of a chaotic. I'm just not recollecting what is the reasoning. But there is this misconception, right? But as far as I can tell, when you're looking to energy levels, right, and you're doing the statistics of the energy levels, if you see a Wigner-Dyson, it is the signature. But for some other observables, I just can't recollect exactly.
And what is this chi?
This guy here is this term that goes in front
the
of
sum of all phases.
Yeah. It's basically, in this model, is what is leading to ups and downs around this mean value. Okay?
Other questions? We already had lots of discussion on this topic also, yeah. But well, I guess that brings us to the end of this workshop on three-body collisions.
Yeah.
First of all, thank you, Jose, and all the speakers of this morning once again. Yeah.
Thanks, everybody.